We'll now look at how to find conditional probability. If you'll recall from our video on dependent events in the multiplication rule, we had this notation for conditional probability, which means the probability of B given A. We're going to assume we know A happened and try to find the probability of B. This results from the probability of both A and B happening together divided by the probability of A. Some alternate notation, probability of B given A, is the probability of A intersect B over P of A. And we'll do a couple of examples showing how to use this. Here's our first example. We had a class that had 2 tests. 25% of the class passed both exams. 42% of the class passed the first. We want to know what the percent of those that passed the first also passed the second. Therefore, we're looking at the probability that someone passed the second test given that they passed the first. Our formula says to start with probability of A and B, so we need to know how many people pass both the first and the second. And that's given to us by the 25%. On the denominator, we need the probability of A, the number of people who passed the first test, which is given to us by 42%. Then we just need to divide these two numbers, and we get 59.5%. So 59.5% of those that passed the first test also passed the second test. Let's look at another example. Let's assume that 70% of people like chocolate ice cream and 35% say they like both chocolate and strawberry. We want to know what percent of those that like chocolate also like strawberry. So we know that they like chocolate, so that's the given part. And we want to know what's the chance they also like strawberry. The top of the fraction is the percent of people who like both, which is 35%. The bottom, the percent of people who like just chocolate, which is 70. This gives us 50% of people who like chocolate also like strawberry. Let's assume we're polling people over a new bill that we want to get passed, and we're going to look at their age groups. Here I have people divided up into 3 age groups, 21 to 40, 41 to 60, and 61 and over. And I have them broken up into 3 categories: those that are for our bill, those that are against, and those that have no opinion. This is known as a two-way table. It can be very helpful for probabilities. As our first example with this, we're going to see what is the chance that someone is against our bill given that they are between 21 and 40. And this given part here is going to be key. We know that they are between 21 and 40. So the only thing we care about in this table is the 21 to 40 row. And we can ignore the rest of the table. In here, the chance that they are against would be 20 divided by the total number of people in this age group. 25 plus 20 plus 5, which is the total number of people in this group. And if we reduce this, we get a total of 0.4 or 40% chance that they are against, given that we already know they are between the ages of 21 and 40. Our next example, what is the chance that someone is over 60 given that they have no opinion? And once again, we're going to look at this given part. We know that they have no opinion, so this time I'm only considering the no opinion column in my table. I can ignore the rest because I already know that they don't have an opinion. We want to know the chance that they are over 60. Well, there are 5 of those at a total of, we can see in this column, there are a total of 30 people. This gives us 0.167 or 16.7%. Now we're going to look at something called at least probability. As an example, if we draw 3 cards with replacement and want to know what is the probability that at least one is a heart. These can actually be very complicated problems. I'd have to start by considering the option of drawing one heart. I would have 3 different cases there, whether I draw it first, second, or third. I'd then have to consider the probability of drawing 2 hearts and the orders those came in, and then finally the probability of drawing all 3. That can be complicated. Instead, we're going to use the complement. And just a reminder, the complement of an event is everything that's not that event. If my probability and my event are to draw at least 1, if I don't satisfy that, that means I drew none. So I can just do 1 minus the probability of drawing no hearts. For my first one, there are 13 hearts, which means there are 39 cards that are not hearts. That's for the first, the second, and the third, since we're doing with replacement. And when we work this out, we get 0.578, or 57.8% chance of drawing at least 1 heart. One more example. Let's suppose I flip a coin 5 times. I want to know what's the chance that I get at least 1 head. Once again, this would be complicated to do out directly because I would need the chance of getting 1 head, and whether it occurs the first, second, third, fourth, or fifth time. Then the chance of getting 2, and I would have to consider order, the chance of 3, considering order, etc. So we would have a lot of different things to calculate. However, the complement, if we don't get at least 1 head, that means we got 0 heads. We got all tails. Anytime we're dealing with the complement, we do 1 minus. Well, the chance of getting tails on the first one would be 1/2. The second's 1/2. Third is 1/2. Fourth is 1/2. And the fifth is 1/2. So now we just need to calculate this. And when we do, we get 0.969, or 96.9% chance that in 5 coin flips, we will get at least 1 head.